Okay, so welcome back to another video. So here we have a definite integral from -2 to 0 of x divided by the square root of x plus 2 quantity squared plus e to the power x dx. And this is actually a very special integral. Well, you might be thinking when I say it like that, like it represents some sort of like interesting form. Not really. I just said that because specifically that the answer to this value contains the golden ratio number. So that actually just makes this video, I can title it golden if I wanted to. So in order to actually tackle such integral, we actually have to do a little bit of some manipulations in terms of simplifying / factoring out some of terms from our denominator. That's the first step, the initial step we're going to take. Then there's actually, of course, going to involve some u-substitution involved. The u-substitution, I feel, in my opinion, the way it actually like works out, because that's when we're going to have to manipulate a bunch of things from our expression before we get to that, is what makes this actually special. And eventually there's we're going to be, of course, utilizing the golden ratio numbers continuing forward as we go too. And actually there's a special integral, like simplifying to that extent, where I'm not going to go to that whole derivation, but I actually did cover on a video covering its antiderivative, which I'll get to that once we get to that point. So other than that, a lot of interesting things going on over here. So why don't we actually just jump right in? So let's start off by factoring e to the power x out of our denominator over here. So we have the integral from 0 to, or -2 to 0. So let's write that as x, and being divided by the square root. So factor out the e to the power x, and then so that's multiplied with 1. I'm just going to rearrange this the opposite, since this is still additions, it's still okay. So then plus e to the -x, and then multiply by x plus 2, and then quantity square, and dx. So with this in mind, why don't we actually now factor out the e to the power x outside of our radical? So in other words, taking the square root of that. And so with that in mind, so we have e to the power x divided by 2 factor out. Why don't I actually put that in terms of the numerator on the top? So that means that's going to be e to the -x squared divided by 2. You'll see why I actually performed this step specifically, because that's where an interesting step comes into play. So 0, -2, and then so now I have and then x times e to the -x divided by 2, and then all this being divided by, so let's see. And so the next step, what I'll do is just to, continue on further, just to take another step ahead. So let me write this as 1 and then plus. So we see here that I have a square, and then what I can do is I'll actually factor out that square in terms of that quantity. So what that means I have is going to be, so inside of our parentheses, we'll have e and then to the power -x divided by 2, and then multiply by x plus 2. We're going to close that quantity off, and that's the quantity square over here. And so what you'll notice is that now the next step is we're actually going to be performing a u-substitution. So the u-substitution being specifically is, I think you could probably take a gander and see what that variable or rather the function we're going to be substituting with. We're going to let u equal specifically what's inside of our square quantity over here. So e and then to the -x divided by 2, and then multiply with x plus 2. Okay. So now to differentiate both sides, so what I have is du is going to equal 2, so that means over here we're going to actually perform the product rule over here. So that means take the derivative of the first function, so I have -1/2, and then multiply by e to the -x divided by 2, multiply by x plus 2, and then add this by afterwards taking the derivative of this and then multiply with that. So that means this is just plus e to the -x divided by 2, and then just follow up with dx. Then let's actually simplify some things even further, such that we can actually perform the distributive property over here. So now I have that du is then simply just going to be equal to -1/2 multiplied by x, and then e to the -x divided by 2. Then add this would just now distribute this over here. So plus e to the -x divided by 2. Rather, this should be a minus since it's the minus over here. So minus, and then afterwards plus e to the -x divided by 2, then dx. And then you'll see that these terms are going to cancel. And then what we're left with is just du is going to equal -1/2 times x, then times e to the -x divided by 2, then dx. Okay, we're not done yet exactly, since we actually wanted to get this by itself, but that's okay. We'll just multiply the -2 to both sides. So now we have a final distribution of, final substitution of -2 du is going to equal to x times e to the -x divided by 2, then dx. Interestingly, as you notice, that's why this is pretty cool to see that I can now factor out, or not factor, I can now substitute this for now our new differential over here, and then put in a new different variable for over here. So now what we have is our new integral is going to be simply written as the following. So now, of course, we change our bounds. So the new integral, so if I plug in, so let's see, I had 0 for x. So obviously we have that numerator that's just going to equal 2. And then if I plug -2 back into over here, that's just going to be 0. And then now we have our bounds. So let's see. So new substitution. So -2, then du, and then divided by the square root of 1, and then plus then u squared du. Or I already wrote du again, so we just get rid of that. And so now continuing forward, that I'll just factor out the -2. So we have -2, and then multiply with the interval from 0 to 2 of just 1 divided by the square root of 1 plus u squared, and then du. Okay, so here comes another u substitution we're gonna have to do. So this is actually gonna involve some trigonometric substitution. We're gonna let u equals tangent theta. So that being the case, that's very easy to see that du is just gonna equal to secant square theta and then d theta. So now we actually just plug in the substitution. So now what we have here is that this is gonna be -2 multiplied by, so plug in our new bounds. If I plug in 2 for u, so that means I have to plug in, so this will be the inverse tangent at 2. And then over here for 0, plug that back in, so that means theta is just going to equal 0. And then what we have is that, let's see, if I plug in tangent theta for u back into over here, so I have 1 plus tangent squared theta. So that's the same thing as equal to secant squared theta from that trig identity. You take the square root of that, I get secant theta on its own, but then plug in that substitution, the du differential, the new du differential over here. So secant squared theta, then d theta. You just divide the secant theta from that denominator, and then we're just left with just a singular secant theta and then d theta. Okay, so this is the integral that I was talking about. So there's it might be a little tedious to actually involve this to solve it for yourself. So instead, I actually cover a video on this antiderivative, very old video from like 2 years ago. So if you actually want to check that out, the link will be in the description below. And the method that I did in that video is actually involved some partial fraction decomposition, which makes it a little bit easier to actually work around with. And it's actually interesting to see. So now, just skipping all that step, of course, as I already mentioned. So what you'll get that our antiderivative, and then we just plug in new bounds afterwards. So what we get here is that this is going to be -2 and then multiply by the ln. And I may actually put in the absolute value for this just to, invoke the positivity of this. So what we have is the natural log of secant squared theta and then plus tangent theta. And then we evaluate our bounds from the inverse tangent of 2 and then 0 over here. Okay, pretty straightforward that if I just plug in 0, then this is actually just gonna disappear to just 0, since 1 over cosine 0, in other words, secant 0, that's gonna be 1. Then tangent theta is just gonna be 0. Then ln of 1, 0, so that's out of the way. So now all we're left with now is just -2, then ln. So just plug in secant of inverse tangent of 2. And if I just plug in tangent and inverse tangent, so then that'll be just plus 2. And then that's all we have dealing with so far. Okay, so we can, if you want, you can probably stop there if you want, but it wouldn't be interesting that you didn't even see the golden ratio number be involved yet, so we have to keep going. So how do we actually tackle such value for secant of inverse tangent of 2? So let's actually draw a little right triangle to actually see the bigger picture. So in other words, let me actually invoke and say that we have data, set this equal to data over here, is going to be equal to inverse tangent of 2. So in other words, that's the same thing as saying tangent data, we set this equal to the number 2. So tangent data, obviously we know that's going to be opposite over adjacent. So that would have to mean that our opposite, so let me put in the data over here, our opposite is actually going to have to be the 2 on this side. Then we have that this is going to equal 1 on that side for the adjacent. So we have a hypotenuse to solve for. So Pythagorean theorem is here to save the day. So that's actually going to yield us with just the square root of 5. Then, of course, we have secant theta, but we know secant theta is the same thing as 1 over cosine theta. So let's suppose we actually find cosine theta for that value. So cosine of theta adjacent over hypotenuse, that's 1 divided by the square root of 5. Then you just take its reciprocal over that and to actually get that value of secant theta. So secant theta in this case, or secant of inverse tangent of 2, is simply just going to yield us with just the square root of 5. I don't know why I said negative. So anyway, this is going to be equal to the square root of 5 over here. So it actually reduces the value a lot easier So now we have negative 2 times ln of the square root of 5 plus 2. I can simplify things even further by getting a little creative and say that I'll actually write this as square root of 5 plus 2 or plus 1, then actually factor out the 2 of that. So, well, rather multiply and divide a 2. So in other words, I have negative 2 then times the ln of 2 times the square root of 5 plus 1 and then divided by 2. You see the golden ratio number over here and then plus 1. Okay, close that off. And then we have now, this is going to be negative 2 times ln. So substitute this for 2 times phi, the golden ratio number, plus 1. And then we can actually use a nice little identity for the golden ratio number and actually simplify things to write this as negative 2 times ln of phi square and then plus phi. So we're basically just adding an extra phi to here to actually reduce this identity over here. We can still keep going further actually. So we have negative 2 and then ln, so phi squared plus 5. I can actually factor out the phi, so that means I have negative 2 ln of, so phi and then times phi plus 1. And then phi plus 1 has a nice identity that's equal to phi squared. So negative 2 and then ln of phi times phi squared, so phi cubed. And in other words, we can actually use the natural log properties to move the exponent outside. And so that'll just yield us with negative 6 times ln of phi. And so that's as far as we go. And therefore, that is our final answer to this neat integral over here. So utilizing the golden ratio number and everything else that we actually have this interesting u-substitution shortcut, not really a shortcut, but interesting u-substitution method that takes us into a nice twist. So everything we see over here, and then it yields us to using the secant data, finding the antiderivative of the secant data, and leads us to the golden ratio number, and then there we have it. So yeah, that's pretty cool if you ask me.